Most robots are docile creatures. They seem to go on their merry own path with disregard of its environment. In fact, if you kick it, it just follows along a brand new path. This robot, on the other hand, is rather special. For when I try kicking at it, it's not bothered by me trying to mislead it in its direction. It always wants to return back to its original path. So how does this guy do that? Well, let's figure that out in today's episode. There is a unique piece of hardware on this particular robot. If you look closely, there's an added chip right above the processor. This little chip over here, it's known as a gyroscope. Very similar to this device right over here. This is a gyroscope. When you take the string and you accelerate the flywheel, you'll notice that the flywheel always remains in the same orientation, no matter how much I turn the base. So that's what a gyroscope is. Back to the robot. So the robot has the same exact thing, except it's digital. Let's see how to code this in software. The software of choice that we use here is Java, as it is often taught in many high schools. First thing you need to do is that you need to import AnalogGyro. And after you've inputted it, next thing to do is to initiate it through this routine right over here. If you're wondering what the 0 is over here, that 0 indicates what channel the gyroscope is connected to, and it's currently connected to channel 0, as you can see right over here. Back to the software now. So once you have imported the package and initiated AnalogGyro, the next thing to do is to read the data, and you can read it through the sample script right over here, where what you're going to do is that you're going to get the angle that's read by the gyroscope itself. Now it's going to show a decimal value, so to clean it up, I'm going to use the math round subroutine. Let's execute the software and see what happens to the robot. I can preview the output by activating prints. So we currently see that the values are 0 to 1. However, if I rotate this a full 360 degrees, for whatever strange reason, it does not show 360 degrees. It only shows 301. Moreover, if I still happen to rotate it one more time, you'll see it does not show up 720. Instead, it shows up 600 degrees. However, 360 degrees is a human-made number. After all, it doesn't have to be 360. I mean, the only reason why it's useful as 360 is because it's divisible by every number from 1 to 10, except for 7. So there are other angle measurement systems that exist out there, such as the radian system. In a radian system, you start off at 0 radian, and after a full rotation, what we know of as 360 degrees, in the radian system, it works out to 2 pi, or 6.28. This robot still happens to be 300 degrees as a full rotation, so we'll roll with it. No pun intended. So the next hack we're going to do is we're going to make these numbers do something useful, such as operate something known as a servo. What is a servo, you might ask? Well, here is a servo right here. It's a device that's actually able to carefully line itself up from anywhere from 0 degrees all the way up to roughly 180 for this model over here. Others may have a greater degree of turn. So we call up yet another import package. This time around, it's the servo package. And like as before, we need to call up a new instance of it. So somewhere down here, we have servo. And this servo over here, we'll call it ServoCam. And we're going to set it up so it's connected to channel number 2. PWM stands for pulse width modulation. It's a method of outputting information. So we'll connect the servo right here. And we'll plug it into PWM channel number 2. Ensuring that black is where ground is and the signal is the yellow channel. Next, let's make this software do something useful with the servo. So this time around, while the software is running its routine, it's going to go off and send off to the ServoCam a value of 0.5 to initiate the center position. And from the center position, we're going to subtract the difference of whatever the gyroscope reads. Keeping in mind that the gyroscope reads roughly around 150 degrees for a full rotation, so we need to divide it by some number that will calibrate it properly. In this case over here, 175 still happens to be the ideal value. Let's execute this code and see what magic it does. So that we can see what's going on with regards to the servo, I'll attach this pen by Velcro to its front. And what you'll see is that as I rotate the robot, this pen keeps on pointing in the same direction. If I so happen to replace this pen by a webcam, now we have a webcam that's always pointing in the same exact direction, no matter how much I rotate it. Not too bad for a homemade gimbal. It doesn't work too well if I spin it too quickly, but if I just gradually spin it, it does a pretty decent job. Next, let's output that gyro data to the robot wheels themselves. Let's see how we code it. I'll run it as an autonomous routine. First thing you need to do is that you want to reset the gyroscope so it knows what the value of 0 is. Here in the software, it notices that if my angle is less than 3 degrees or 3 parts out of 300, what it'll do is that it's going to slow down one of the wheels and speed up the other wheel so that it can straighten itself out. If it notices that it's beyond 10 degrees or 10 parts out of 360, it will aggressively speed up the slower wheel so that it can catch up. However, as you may have noticed in the beginning of the video, I kicked the robot rather hard. So that's an angle that's beyond 10 degrees. What it'll do is it'll stop the robot and start to rotate it. It'll rotate it first in the direction back to 0, and if it overshoots, it'll slowly correct it back. I'll provide a copy of the software in the description below. Well, that's it for this week's adventure. If you want to see more crazy stuff like this, make sure you click that like button and subscribe to my channel. Till our next adventure together, let's kick the robot one last time. Yeah!